But yeah, so for today, we're gonna let me see, make sure I can get my screen share right. Uh, share. Okay. So y'all should be able to see the slides. Okay. All right. Yeah, so today, so we're gonna do the plan is to do two chapters. If I start going too fast and we need to slow down, that's fine. We can just do the one chapter and then leave the other one for later. Because I don't want anybody to feel rushed. But these things, I think there'll probably be some later ones we might want to need to split into two because it's just too dense or, I don't, or I like to be efficient. But yeah, definitely don't feel overwhelmed if it's going too fast. We can stop. Okay, so what we're going to talk about today is collections and specifically more common collections in Rust. So there's kind of three key ones that the book identifies as like the most common ones. That's what we're going to talk about. Um, we want to know kind of their collections are kind of stored a little bit differently than the variables we talked about so far, and there's some important reasons for that. And then we'll talk about how to get out single elements of a collection and how to iterate over it. Um, and then yeah, talk about like some of the other different types of collections that Rust has and how to get more information. All right, so in kind of a nutshell, collections are these data structures that can hold multiple values. So far we've mostly looked at like string slices, which is kind of just the single string. Integers holds one integer value, floats holds one float value. So collections is the kind of general Rust term for mean like a container for multiple values. So an integer would be like a single value, but you could have a vector, which is like a collection of multiple integers. And we've already kind of talked about arrays and tuples. They are they do hold multiple values, but they're a little bit different than collections. Arrays and tuples are like fixed size and they need to be known like at compile time, versus collections can grow and shrink over the lifetime of the program. And so you don't need to know exactly what size it is ahead of time. Oh yeah, some bullets there, sorry. So yeah, they because collections are sorry, so like arrays and tuples and things are stored on the stack part of memory, and then collections are stored on the heap part. So we don't have to know exactly what that means, just they're two different kind of places to store things in memory. And these collections are stored on the heap, which means they can kind of grow or shrink and change as the program goes on versus needing to be like a fixed size, fixed values at compile time, which would be you're raising tuples, but collections are variables. So the three common types of collections are vectors, strings, and hash map. So vector is it's kind of like a vector in R. You could have integers, double or I think floats in Rust. Um, they can only hold one type. A string is like the capital S string that we talked about before. Um, and then a hash map is like maybe like a named vector in R, a name list, or like a dictionary in Python. So it's just like it's a set of key value pairs, uh, or like an object in JavaScript is similar. Okay, so we're gonna start with vectors. You can kind of create these in you'll see this kind of pattern. You can create these in two different ways. You can use new and then add to create, an empty vector and then add values to it with push. But I think more often than not, we're going to use the this macro vec exclamation. And that's basically like using C and R, right? You just put in your actual values that you want there. And if you notice, so on the right-hand side, we just have let V. On the left, we have let mute V, just like everything else in Rust. It's going to assume to be immutable by default. So you have to make sure if you might need to change it later, you know you're going to need to change it, you specify as mutable. And so we have two ways to get elements. We can use like square brackets, like we would um, vectors in our data frames, like we would index into an array. And we have the get method as well. So when we use the square, um, sorry, one sec. Yeah. So the get method it's not going to return the same type, and you can see by the types here, it's going to return an option of like an option that the underlying value is a reference to whatever the type of vector you have. Um, might be a little confusing, but the main point is it returns an option. So what that allows you to do is say, let's say I specify something, an out of range index. If I use the square brackets, you're not going to be able to do that. It's gonna crash because like that's a dangerous thing to do because you could, if you access something out of index, it could be accessing a portion of memory that you shouldn't be able to access. So what the get method does is says like, okay, this could have some value or could have none value. And that way you can say, okay, well, in my case, it's not a big deal. If somebody tries to access the 100th element of a 10 element vector, I just tell them to do it again, like choose a new value. Um, and so there's and it can, ownership and borrowing all that. I suspect some of you are the same as me where that's still kind of really confusing, but the way it comes into play here. So this program here, so you might think it would compile because we create this vector of length 5. We access the first element at index 0, excuse me, and then we push a value to it, but we push it at the end, right? So it doesn't really affect index 0 because it's not adding to that first position. It's going into the tail end of the vector, and the vector is mutable. But Rust isn't going to let you compile that way. So the reason is because like Rust stores a vector as like one single block in memory. And so once you change the vector, so this line 5 where we're pushing a new value, it could be that you just take the next section of memory and it goes there, but it could be has to be copied over to some other section of memory in order to hold hold the entire vector in one continuous block. So if that happens, then this variable first in line 3 is trying to point to that old spot of memory where the first element originally was. Um, and you don't know if it's going to have to copy or not. It only happens at runtime. So Rust isn't going to let you do that. So yeah, I guess the main point is just kind of be careful of like how you're using it. So this is something that the compiler will catch and give you an error message you can help trace down. Um,
Check my understanding. If I commented out the print line, it would work, right? Because it actually the reference would no longer be
yeah, because you're not trying to use it. So that should be.
interesting.
And so we have these collections. We're probably going to want to iterate over them. And so there's a couple ways to do this with vectors. So you can have immutable vector, so we don't specify the mute, and then you could also have immutable it's reference to the element, immutable elements, essentially. Okay. So we have this vector 1, 2, 3, and our in here is ampersand v, meaning like for each like using v as a reference. So it's kind of pointing to going through each one of the values in v, and we'll look up like where that's stored. Um, so in this case, like you're gonna get what you expect, so just printing all the values. If you need to change things though, that's where you have to use both a mutable vector. So on line 1 here, we have to specify let mute, and then on line 2, that reference to the each element of our vector has to be mutable as well. So we have to say, so basically it's saying I is a mutable reference to an element in V. And so once we have that, then we have to dereference the I in order to change it. So that's what that asterisk is. And then we can do something with it. So in this case, we just add 1, and then if we go through in the same way, print out each element, and in the second loop here, can you guys see my mouse? Yeah. So this second iteration here is the same kind of iteration here. So like we could, in this case, we're just printing and we don't need to actually modify anything. So we kind of have to just be careful like what you're doing. So in this case, when you print, it's gonna print 2, 3, 4 because it's adding 1 to each element. So yeah, if you need to change the values, just you got to put at mute the thing you're iterating over, and then you have to use that value, you have to use the dereference operator. Which I believe what that's going to do is instead of that I is instead of in the first case, it's kind of pointing it's like a location in memory versus the second case when you use the ampersand and the I here is going to go into the memory to that location and actually pull out the value. So vectors can be only one type, but sometimes you might want to store the multiple types in there. So you can't do that, but you can use you have to use something like an enum or a struct. So the example they gave is a spreadsheet cell, which I think is a good one. So you could have maybe you want ints, maybe you want have floats, maybe you want have strings. You can still keep that in a vector where just each element, instead of each element being like the int and the float, it's a enum, one of the I forget what they're called, one of the factors of the enum in our language speak. And same thing with, you can make your own structs. So in this case, it's an example struct. You can have maybe a number and a string, and you create the struct just like you would, but then just wrap it in vector here. I think typically you probably wouldn't do that with vectors, my understanding, but it's doable. Okay. So that's any question on the vectors? Okay. So the next thing is strings, and I think strings are kind of like dates, and like they're really complicated, and they don't like seem complicated. We've already kind of talked about strings before, so I'll try to kind of keep to new things here. So strings, the collection, string is a collection. So note there's a capital S string versus all lowercase str. That's something different. But a string is a collection of bytes. That's how Rust stores it. And it's in the Rust standard library. It's actually built kind of like a wrapper around vectors, where each element of the vectors is a byte. And then Rust uses UTF-8 encoding everywhere. So we've kind of talked about a little bit about string and um, a bit about str. I don't know how you say that, string str. Um, but just kind of the differences here is a string would is like a vector, and then an str is like a slice of that vector. And typically you see str as like ampersand str is like you're using it as like a slice that you're pointing to like a reference to something else. So str is built into the language. String is actually not in the language itself, but in the standard library. And then I think the main thing to me is their size can be dynamic. So with a capital S string, you can append you can append more text to it, but with a lowercase str, it's a fixed value. Mm. Oh yeah, and so I was kind of confused about this, and I don't know. I think it's still a little bit confusing. Exactly, I feel like I don't 100% understand. I did find there's two links down here that kind of help explain it. Um, so like if you're interested in kind of getting a different explanation or better understanding, go check these out. I think it's okay to just be like, okay, there's these two things. Like that's fine. We don't have to know like the intricate details of why and what the differences are. And so similarly, you create string with new, which again we've seen that string new. You can put your actual text string in there, and it'll create that for you. Or you can do new with an empty, and then you can push str to push str type into it. You can also put the text directly in there, or you can just have the text and then call .toString, and that will turn it into this capital string. You can there's kind of two ways to combine strings with the plus operator. So I think Python does this, JavaScript, and then you have the format macro, which would be more like your glue, or I think Python calls them f strings. But where essentially you put some brackets there and put the variable that you want to print out there. So yeah,
What?
it replaces the value before it prints it out. The question?
Yeah, why would on the plus example, like let S3 equal S1 ampersand plus ampersand S2?
Yeah,
I
that's a
get
great
this.
question. So it has to do with how add is defined in Rust. So it's kind of just like a consequence of like how they designed it. So the way add works is it takes a self and then it takes a reference. So self would be like the thing on the left, and then the reference it has to take a reference on the right hand side. So
So if you
basically,
flip
it's not
it, you would
overloaded.
just have to put S2 and then plus ampersand S1.
Yeah,
Okay.
and same thing, anything after the first, you could have five pluses here. You have to put that ampersand there. And the book does talk about it a little more in detail if you want to check that out, but you just have to remember to put the amper there. That's
Well, I guess the
pretty
key
sufficient.
observation is that the S1 is moved and S2 is not moved. Instead, it's taken by reference and actually copied into S3. So S3 is whatever S1 was plus S2 added on, a copy of S2. With format, you get copies of everything. None of the S's are affected. None of the other S1, 2, whatever aren't affected. Only you just get copies. They're all references, even though they don't look
So
like it
That
because it's
makes
the
sense.
macro. The macro sneaks in references.
after in the plus example, if
Hmm.
after line 4 you added like a println S1 and a println S2, I
Would
guess would you
compile.
get a compiler error for the println
Yeah.
S1, but you wouldn't for the S2?
Yeah.
Yes.
That's my
Yeah,
understanding.
yes, I believe so.
I'm gonna give it a shot right now. One
Yeah,
sec.
Show
I
you in the
can
Rust
check it in
playground and
the
check it, but let's know.
yeah. Um, yeah, get back to us. That's a good question. Yeah, so to access element, so you can't in short, you can't really do it. You can't access like pick out like I want to take this character or that character. Um, the reason is just kind of how Rust stores strings. So like we said, it stores it as like a vector of bytes. But languages are different, human languages are different, right? And so, in English we might say HELLO, like, okay, give me the second element. I just want to say, hello bracket 1, and that might make sense, but in other languages it's going to take more than 1 byte to store a character, or I think they reference like grapheme. I'm not a linguist, but the idea of like, the equivalent of kind of letters. So it doesn't make sense. It doesn't always make sense to try to, pick the fifth element. So Rust just says you can't do it ever. So if you print what if you print these, and there's a link here to the Rust playground for that. You'll see that hello here is length 5 because it has 5 bytes, and then konnichiwa here is length 15 because it takes 3 bytes to store each one of these characters.
Yeah, confirmed. S1 won't print, S2 and S3 will.
Thank you. So we can't pick out one element of a string, but we can kind of cheat by using slices and just having that slice there. But the way we can kind of do this, so in order to index into strings, we have to specify a range. So, the 0.1 or 0.5, however far we want to get into it. But it's not always going to work it's not always going to work right the way you think it is. It depends on the language. So you kind of have to know how many bytes it takes to store like 1 unit of that language. The book has an example of German or not German, Russian, where it takes like, I think 2 bytes to store each one of the characters. So to me, it just seems like you probably never want to do this because it's just really risky. You have to know exactly, how Rust handles each language, or how UTF-8 encodes it. So just be really careful. Yeah, and sorry. So there is a link to the Rust playground here for Konnichiwa. We can't pull out this first character. It doesn't make sense. Because it takes 3 bytes to store it. You're right in the middle of the definition, so Rust is going to complain about it and say no, like you can't do that. And then there's 2 ways we can iterate through strings. We could pick out the characters or the bytes. So you got to kind of know about the language to know, how many bytes you want to get out of it. Characters is going to be, or this dot cars is going to be a little bit closer to what we would kind of think by looking at it. So in this case, it'll print the H, E, L, L, and then O. And then for Konnichiwa, if we pick out the characters, it's going to be each of those 5 characters. I don't actually know Japanese, so I don't know which writing system this is, but yeah. And then if we print out the bytes, it's just going to be, so this in the case here, like we said, it was 15 byte or 5 bytes for hello. So you're going to see those 5 bytes printed, and then for Konnichiwa, you're going to see all 15 of those printed. So yeah, in short, strings are complicated. So just be really careful, and until you're really familiar with how Rust implements strings and how it stores strings, you got to kind of understand that in order, I think to really work, if you're going to work with strings a lot. So the last common collection is hash maps. And so it's a key value pair. So it'll look something like this. So although it's in the standard library, you do have to import it because it's not as commonly used as vec and string. Those you don't have to import. but the hash map you do.
Just to clarify, you're not actually importing it. You're just creating a shorthand, right? It's
Yeah, yeah, it's like the other ones are in like the prelude. Yeah,
You could always keep writing standard collections hash map everywhere and you'd be fine, but you know what
yeah.
I'm saying? It's just creating a shorthand.
Um, yeah, so do you use new just like vectors and strings? And then if you want to add values, you need to use insert. Okay, so it'll insert the key. The first element is the key, and the second is the value. Um, so yeah, the key and value can be of whatever type you want. It just has to be consistent across the whole thing.
I think there has to be hashable types on a key though.
Yeah, yeah, because yeah, that makes sense. Thank you. Um, and so to access elements, we use the key. And it's a little bit more complicated than something like a vector. So this is just kind of creating the same string, these first few lines. We don't have to necessarily create this vector for blue team, but we use the method get, and so we say get, and then the key that we want, and then that returns an option. So what we do, this extra lines here is just like, okay, I'm gonna actually copy that value. That's the underlying value in the option, and this unwrap or has to do with like errors. So what it's saying is if there's not actually a value there, so if it's a none, then give me 0. So this is just kind of just making sure it'll actually print something. Um, but in this case, there's something there, so the blue team has 20 points is what it should print out. Oh, yeah, sorry. A little more here. Yeah, so get returns an option of type um a reference to the value type, and then copy is going to return that actual like value instead of like reference to the value. In this case, it'd be I32, and then unwrap or 0 is just going to be like, hey, if there's a none there, then give me this value instead. And so we iterate across the pairs of keys and values. So for key, instead of like just for I, we have to say for key value. And scores, we can get all the keys and values. The thing to note here, though, is the order is not necessarily going to be the order that you inserted them in. There's no real order for hash maps, so you can't rely on the order of things when you're iterating. And then once we have if we have a mutable vector, we can update it again. We will use generally we use insert, and that'll overwrite any of the values there. So if those already exist, it's gonna just replace it with this new value. Another way you can update hash maps is like if there's not a value there, then I want to add it. Otherwise, if there is, I'll just leave it as is. And so that's what this does. So if in this case, we're inserting the key blue and the value 10, and that's all that's in our hash map. So when we get here, we say we use dot entry. When we get here and say I want to insert red 50, what's going to happen is it's going to look to see if red is already a key. If it is, it's going to skip. In this case, red is not a key, so it's going to add the value 50. So it'll be, you're going to have 2 items now, but on this blue case, it's like, nope, like that's already there. I'm going to skip you. So blue would still remain at the value there would be 10 instead of this 50. And the kind of last way you can do is modify an existing value. So yeah, I mean, this one's it just goes through and counts all the characters counts all the letters in this text. Okay. So for each word and splitting on white space here, we're going to count the letter if we haven't seen it before, kind of thing. So we use like we saw before, use a dot entry dot or insert. So that word is not in the hash map, we're gonna assign a value 0, and then we're gonna increment the count. If it is already in there, then we're just gonna increment the count. And then so the last thing is I just wanted to point out like the documentation page on collections is nice. So it has like all the other methods for like the 3 collections we talked about today, but it also lists out all the other types of collections. I think like set is one type. But the main thing what I think is really cool is they kind of give you some guidelines of when to use what type of collection depending on like what you're doing. So I feel like it's kind of like a little bit of like type overload with all these options in Rust, all these different kind of types we use. We use a custom one, but so I really just really liked how they kind of pointed out and guided you of like, okay, if you're doing this, you could probably get away with a vector. I mean, in short, it's generally like you're going to want to use one of these 3 types unless you know you need to use something else. Awesome. Any questions? Okay, I'm gonna get my so I can get my thing set up again. Okay. Whoops. Sorry, I'm not much of a technology. There we go. There we go. Okay. We can see it now, yeah? Oh, no.
No.
Gotta click that final thing. There we go. That should be good, yeah? Okay. So the second chapter here is about error handling, and there's not much to it. I think it's pretty straightforward. The book has a lot of details. But honestly, like we're at the beginning stages, a lot of that probably doesn't really matter for us yet. So there's kind of what we're going to focus on today is just make sure we know what the 2 types of errors are, and like kind of have an idea of when to use which type, and then how to know how to work with the result enum. So the 2 kind of types of errors are recoverable or recoverable errors. So unrecoverable would be like stop, or like you want to stop the program, you don't want them, you want to shut everything down. You shouldn't be allowed to continue. Recoverable errors are things where, like that guessing game we had an input, if they put in a value outside, you want a specific range, but you can just ask them for another value. That's fine. So recoverable errors are like you don't necessarily need to stop the program. You can kind of work around with it if it does end up in an error. So there's no exceptions in Rust, which is kind of interesting. You basically just have panic, which is that unrecoverable error, so it'll crash things, and then you have the result type. And so this T and E here, T is the type of like the data, and then E is like the type of error. And so this like notation, I think it's come up a couple times. I think this is part of like generics, I think is what they call it in general, which we'll kind of get to later. But generally, I think whenever we see a T, it's like the type. And then in this case, it could either return an item, it could return an integer or a float, for example, or it's going to return an error. So that's kind of what result is indicating. So yeah, it's those are the only two options. You can't do like a warn or a message or anything like that. It's just you're gonna work around any possible error, or you're just gonna say no, I'm not allowing that. So yeah, panic is pretty straightforward. When you put a message in there, it's going to print the message, clean out the stack, and stop the program. If you do need like more of a backtrace, you can set this environment variable, and it'll print, the series of function calls that led to that. Um, and they do mention like if in certain cases, like maybe in your actual like deployed binary, you want it to be smaller. One thing you can do is set panic equals abort in your cargo.toml. And what that'll do is like not it won't clean up after itself, basically. But it allows your binary to be a lot smaller. Yeah, and the main thing is result. So it's an enum. Again, so we have this like TE here, so it's either going to have type, it's going to be okay, whatever type you have, or it's going to be an error with like whatever type of error you have. So T is like the unsuccess, and then E is like the failure. So the example they use in the book, and I'm going to use here, I think it works well, is like reading something from a file. So in this case, your T is going to be the standard FS file, and then your error would be standard IO error, because that's what file open is going to return if it doesn't, if it can't find the file, if it doesn't exist. And so these really just kind of depend on what your function that you're using returns. So um, what we need to do to be able to handle those two cases is this. So this file open is going to return a result. So there's two possible things that can happen here. So what we can do is, like we saw before, use a match, and we go through all the possible values of our enum. So if it's okay, then it's going to have the file object there, and that's what we want to return. If we get an error, one thing we could do is just panic and say, okay, there's an error, I don't know what to do. So yeah. But what we could do is there's certain cases where like maybe we know what to do. So for example, if we know that like the file isn't there, then we can maybe want to create the file. And so we can kind of this first part is the same. Like we want to say, okay, like, yep, return this file, it's all good. But then if it errors, we want to look at the kind of the error, like what type of the error it is. And if it's a not file not found error, then I want to go ahead and then I want to create it. Now create itself, this file create is going to return a result type as well. So you have to handle the okay and you have to handle the error. So what we're saying here is like, I want to try to create the file. If it doesn't work, then I want to stop. I want to panic. If I get some other type of error, I don't know what to do, so I'm just going to crash the program. And I remember to have notes on here outlining that. So wait, so yeah, there's a couple of shortcuts you can do. So you don't have it's kind of verbose to write all those matches. You could maybe use like if, and that could work. But Rust provides this thing called unwrap, and it's gonna do basically what we just had there. If the value if you get an okay, it's gonna return that value. If you get an error, it's gonna panic. And then within the other option here is accept. So or sorry, expect. So try to read this file. If it works, then okay, return the file. If it doesn't work, then I want you to panic, and then this is what I want you to tell them. Say, hey, this file needs to be there.
I just want to say, can you go back for one
Yeah.
second? I love this so much, the unwrap method part of this, because like when you're lazy and in development and doing your first iteration of code, you just throw unwraps everywhere and get the thing working and prototype, and then it's so easy to review exactly where you need to figure out how to do your error handling properly, and you
Yeah.
can do one pass through getting the logic into the program, and then a second pass through just handling all the unwraps, and it's
Yeah.
such a nice kind of workflow for um yeah, just for building better production code. It's I really like it. It's cool.
Yeah. That's awesome. I could see it being, yeah, really useful for even just like checking, I guess you don't really need to do in Rust, like in R, for example, like you might want to check like, hey, is this value there? Is this actually one of the allowed values? There's a lot of that, like stop if not this or that. And like, it just gets kind of it gets, to me, a lot of times it gets complex and people just don't do it because it's very tedious. Um, but yeah, this method seems like, I don't know, a little bit easier to do, a little bit more robust.
It's just nice to be able to hop into a code base and just do a global search for unwrap and just fix it
Just
all.
find where you're,
Find all the places that you're not handling your exceptions properly.
it's like a built-in to-do comment.
Exactly. Yeah, it's kind of convenient.
Yeah, so one thing you might want to do is like bubble your errors up. So you have some sort of some error, but like you don't want to deal with it within that function, so you'll pass that up to the calling function and then let that decide. So it's yeah, it's kind of like if you have some operation in your function that could error, you might want to actually just return that error instead of, maybe you don't have enough context to handle it within this function. Um, so the example here is like trying to read a file. You can, let's say if you try to read the file and you get an error, you can just return or do an early return, right? None of this will run. And then if you notice here, what we're turning instead of, um, I think it was the file, we're returning a result with type string. So if it's good, it's going to be a string. Otherwise, it's going to be an IO error because that's what your file open is going to return. So assuming that's okay, then the example here's like they're trying to go into a file and actually pull something out. So pull a username out of the file. Um, we can say, okay, if we read that to string, it's all good. We find this username, then we're going to return okay with the username. Otherwise, we're going to turn an error. So, I mean, this example is probably, I don't know that it matters too much, but the way I think of it is like, maybe if you don't have enough context within the function you're working with to decide what to do, you pass that up and let your calling function figure it out. And so the reason to bring this up is because there's a lot of shortcuts to simplify things. And the question mark is one way to do that. So it's like an operator that you put at the end. So instead of having, all this match to go through an okay and error, we can add a question mark at the end, and it's going to do the same thing effectively. So it's gonna return okay the contents of the file, or it's gonna return the error. And similarly here, once we go into that file and try to read it, if we got this question mark here, it's gonna propagate any errors and early return. Otherwise, we're gonna okay the username and return that. And the book has like two more examples of making this even shorter. So I think it's worth looking at if you want, but it's not so much about like errors and results and versus just like shortcuts to make your code a little bit simpler. Um, and it's kind of like more about the particular methods of the FS crate than it is kind of on topic here. But you can't always use this question mark operator. Um, you can only use it in situations where the function, so the operation you're doing within the function, your function has to return that same type. So if you're writing a function that returns a result and the inner function that could mess up returns a result, then it'll know what to do. Um, Otherwise, you're going to have to handle that somehow.
Does it have to return like, do the T and the results have to be the same, or can it be an arbitrary result type?
I'm
They do have to be the
No,
same.
yes, they have to be the
Um,
same. And the example here
unless,
is,
yeah, they give an example where you can like use some kind of box dynamic. I don't know how that means yet, but
yeah,
Yeah, there's a whole chapter on that later that's confusing as
yeah.
hell.
But so let's say we're trying to, if this isn't our main, um, we can't just call it, we can't use it here
Mm,
because main is you can have that type, I don't know, null or I don't know exactly what it's called, but like
yeah,
unit.
yeah. Makes
But file open is going to return a result. So the types don't match, so it's not going to let you do that.
Yeah, for sure.
you can define main so that it does have that type,
Yeah.
that box dynamic error, whatever.
Um, yeah, I mean the book talks a lot about like when to use, when to not. I mean, it's really just gonna
Yeah.
it's hard to really say anything because it's gonna depend a lot on your context.
There was a lot of text on that. I was just kind of
Yeah,
surprised. Like, whoa.
it's like okay, cool. It's one of those I feel like it just sometimes it tries to do a little too much for a beginner level where it's
Yeah.
like that's good to know, but it's not really relevant yet.
Have to read it again
Um,
later.
hmm So I think the main things for panic for me would be like I can't guarantee the correctness of the program or it's safe, if this error happens. And then like Jackson was saying for like
Yeah.
examples and prototypes and tests and stuff, they recommend basically just using the unwrap, which is going to panic, and then kind of build your way up from there because it's not worth going through all the trouble to do that when you're just writing initially kind of exploring and seeing if something will work. Awesome. No, that's all I got. Any questions, comments?
Maybe just a comment. I imagine the that section was so long just because I guess if Rust's main value add is that it's like so safe that they need to document all the reasons that it's so safe and how to
Yeah.
use it safely. Yeah, it's pretty cool stuff.
Yeah, it seems interesting. Let me put in the chat. Oops.
Does anyone know? Like, I mean, that's a later chapter, but do tests like is panicking a proper test